Hi there, and welcome to this lesson. In this lesson, we'll be learning about quantities and units. Okay, so we're learning about quantities and units, and we will be learning about natural and derived quantities and units. Now, as the lesson progresses, anything you don't understand, be sure to get across to your tutor, who would be more than happy to help. And yes, let's jump right into the lesson. So quantities and units, natural and derived quantities and units. Now, a natural quantity is a quantity that exists in nature. Okay, so a quantity that occurs in nature. And basically you just have quantities that are just quantities in terms on their own, by in their own right. Okay, so you have things like mass. The mass of a body is the amount of matter that that body contains. So you have mass. Mass is a quantity just on its own. It's a quantity. And then you have length. Length is measurable quantity. Length is a measurable quantity, and basically you have a quantity that just exists in itself. It's a measure of the distance from one point to another. And then time is all around us. Time is a natural quantity. Now, the other type of quantities that we have derived quantities. Now, a derived quantity is a quantity that does not exist in nature, but is derived from two or more natural quantities. For example, we have velocity, acceleration, and density. Now, velocity is not a measurable quantity in itself because velocity comes from length or distance and time. It's a relationship between distance and time. It does not exist. Velocity is not something that exists in nature, but something we derive from distance and time. Similarly, acceleration is from distance, velocity over time, and basically that's distance and time again, basically. And then you have density. Density is mass over volume, and basically even volume is a derived quantity. Density is also a derived quantity. And yeah, that's pretty much the difference between a natural quantity and a derived quantity. A natural quantity exists on its own in nature. It's something, it's measurable in nature, but a derived quantity is, we get derived quantities from two or more natural quantities. Now, let's talk about units, okay? So the unit of a quantity. Now, these are some common quantities and their units. So we have mass, and the unit for mass is kilogram. Length or distance or displacement, the unit for that is meter. Time is second. Electric charge is coulomb. Okay, very interesting name there, coulomb. And temperature, we have Kelvin. So there's just a few quantities and their SI units. And then we'll talk now about prefixes of quantities. And sometimes, or prefixes of units rather, and sometimes we have certain units that are expressed to a certain scale. Okay, I'm just going to bring in this table to tell you exactly what we're talking about. So for example, you have gram as a unit, and then 1000 gram is a kilogram. Okay, and sometimes you could have a coulomb. Okay, and then a coulomb times 10 to the power of 12, that should be, I think that is a trillion coulomb. We say a teracoulomb. Okay, one very common one very common common one very common prefix we use bytes. Okay, so you have a byte, you have a kilobyte, you have a megabyte, you have a gigabyte, you have a terabyte. Okay, and a terabyte is a byte. You know, there is a special calculation for bytes, basically when you're doing computers, but generally you get the idea. Basically, it's about 10 to the power of 12 of a byte. Okay, a gigabyte, or when you're talking about giga, is 10 to the power of 9. Mega is 10 to the power of 6. Kilo is 10 to the power of 3. Okay, and then when you go in smaller, basically B's are for big numbers. Okay, when you go in smaller, 1/10 of a particular quantity is deci. Okay, so you have decimeter is a tenth of a meter. You have centimeter is 100th of a meter. You have millimeter is times 10 to the power of 1 over 3. That's divided by 1,000. So you have 1,000 millimeters in a meter. You have micrometer. Okay, so micro is 10 to the power of 6. Okay, micro is actually quite popular. And then you have nano. Nano is also quite popular. So nano is 10 to the power of minus 9. Okay, I think we do have 10 to the power of minus 12, and that's pico. But let's go ahead. Let's go ahead. So now that we've talked about quantities, we've learned about derived quantities and natural quantities. We're going to talk now about derived units. Okay, and something very interesting about derived units, we can make up units for derived quantities based on the quantities involved, based on the quantities that they're derived from. Okay, so if you have a derived quantity, you could find the derived unit, the unit for that quantity, based on the units of the quantities that that derived quantity is derived from. What are we talking about? Basically, if volume is length times length times length, now volume is a derived quantity, okay, and the unit for length is meter, find the unit for volume. Basically, you have volume as length times length times length. You apply that quantity to the formula, okay, and the quantity, the unit, you apply that unit to the formula, and basically the unit for volume would be the unit for length times the unit for length times the unit for length. In this case, we have meter times meter times meter, and what we have in the end is we have meters cubed. Simple, that's it. So the unit for volume is meters cubed. Now, what if you have density? Okay, so density is mass divided by volume, and the unit for mass is kilograms. The unit for density is meters cubed. Asked to find the unit for volume is meters cubed, and we're looking to find the unit for density. Okay, the unit of density, and what we have is unit of density equals kilogram, because we have that density is mass over volume. The unit for mass is kilogram, unit for volume is meters cubed. So we have kilogram divided by meters cubed, and what we have in the end is we say kilogram per meters cubed. Okay, or kilogram m to the power of minus 3. So per meters cubed is same as to the power of minus 3. If you have per meter squared, it will be meters to the power of minus 2. If you have per meter, it will be meters to the power of minus 1. Simple, straightforward. Now let's do one that's fairly more complicated. Okay, so we have linear expansivity as the change in length per unit length per degree rise in temperature. Okay, we have that the unit of length is meters, the unit of temperature is Kelvin. Find the unit for linear expansivity. So this is the formula for linear expansivity. So we have length at the top, okay, and we have length at the bottom, and we have temperature as well. So change in length still has the same unit as length. Basically, 10 meters minus 2 meters equals 8 meters. We still have the same unit. So what we have, we have meter at the top, and then meter at the bottom, and then Kelvin. Now the meter would cancel meter. Basically, you just do it like standard algebra. So meter cancels meter, and what we have in the end is we have per Kelvin. So the unit for expansivity we say it as per Kelvin, or Kelvin to the power of minus 1. And yeah, that's it. Very simple. Now, finally, let's talk about some derived units with special names, okay? So we have some interesting units that have special names, one of which is force, okay? And some of these names, they usually come from, for example, I think the scientist who did the most experiments on force was Isaac Newton, okay? And that's why the unit for force is newtons. Frequency, frequency is the number of times something happens in a given the number of times something happens in a given span of time, okay, and the unit for that is hertz. Pressure, Pascal. Pascal is someone's name as well. Energy, Joule. Okay, so we measure energy in Joule. Now typically force is mass times acceleration, and typically you'd have force as kilogram meter per second squared. Okay, kilogram meter per second squared. But then we write that out as newtons. Energy you'd have as force times distance. Okay, so what you would have kilogram meters squared per second squared, okay? But we write that down as joule with just a J, okay? And those are some derived units with special names. And that would bring us to the end of this very simple lesson. If you're going to take anything out of this lesson, you remember a natural quantity, one that exists in nature, a derived quantity, a quantity that's made from derived from natural quantities. You have the different SI units of some of the popular quantities, common quantities that we know, and prefixes, very very important. Okay, um, particularly when you're dealing with very very large numbers. Sometimes you may do some calculations, and let's say you're getting a number in meters, and you end up with 0.00000074 meters, and you would be best to express that in terms of micrometers or nanometers or whatever you have there. And then you have derived units, how to form units for derived quantities based on the units of the natural quantities that those derived quantities are derived from. And finally, just a few derived units with special names. So we have force as newtons, frequency as hertz, pressure as Pascal. Pressure is force over area. So pressure typically should be Newton per meter squared. We will write that out as Pascal. And finally, we have energy as joules. And yes, that should bring us to the end of this very simple, very interesting lesson. You can go ahead now and attempt questions on the worksheet. Bye for now.